So, welcome at my last lecture, in general last but one lecture, and the topic of today's lecture is virtualization. So we are switching back from Java, and we are not switching to C or anything like that. We are more or less switching to hardware. So it's again a topic which is more low level, perhaps more approachable from C, C++, and those lower level languages, but it's mostly about hardware. And the topic is, of course, virtualization, as you can see. And what we plan to talk about today is first what virtualization actually is, how it is used, and so on. I guess most of you already know these basic things. And then we will look at how hardware-assisted virtualization works. Hardware-assisted suggests that it is like hardware-accelerated, hardware-assisted. That's true. It's fast, but still there are some things related to memory accesses which are slower than if you use non-virtualized environment. So it's good to be aware of this fact because it can somehow change how you what you prioritize when you optimize your software. And the second part of the lecture will be devoted to I/O virtualization. Whenever you are developing cloud application on whatever, you do a lot of I/O, meaning typically a lot of network communication. So we will talk about some hardware, how does the hardware work, which allows efficient I/O operations from inside of virtual machines. So let's start. Virtualization basics. We will talk about virtualization, and by that we mean virtualization of the whole computer platform. The thing is that the software which will run on our virtualized platform will think that it runs on physical hardware, but the hardware will not be physical, the hardware will be virtual, and the virtual notion of the hardware is provided by hypervisor in cooperation with virtual machine monitor. So we will look more into detail what those two terms actually mean. But before we do that, just another clarification: you had a block of lectures about Java. So maybe if you hear the term virtual machine, now you think Java virtual machine. So no, we are talking about non-Java virtual machine. In Java, virtual machine was a software concept where this software called Java Virtual Machine either interprets Java bytecode or executes precompiled code and provides some kind of interface for the Java application, like mediation between the Java application and the operating system, let's say kernel. In our case, we will mean that virtual machine is a concept which executes whatever code, typically full operating system, and the virtual machine interacts with the hypervisor, so not with the user level software Java Virtual Machine, but with the hypervisor and virtual machine monitor, which is another software. Virtual machines are nowadays used everywhere, not only in clouds, but also like if you are developing on your computer, you need to develop for different operating system, like on Windows you are developing for Linux, so how is it called? WSL, this is actually a virtual machine which is quite hidden inside Windows, but technically it's a virtual machine. And so this is nowadays it's everywhere, but it's actually very old concept. It was developed in 70s last century from people by IBM mainly, and it was used since then on like typically mainframes. The reason why it appears more modern today than in last century is that x86 architecture, which is quite common nowadays, this in the past it was not fully virtualizable. In the past, if you want to run virtual machine on x86, it was quite difficult and slow and so on. But fortunately, since it's already like 20 years, when Intel fixed their hardware, and now even Intel hardware is fully virtualizable. This lecture will somehow talk about more advanced topics, so if not sure about you here or people at stream, but if you didn't have operating system course, I suggest, if you don't understand anything in this lecture, I suggest looking at the slides for the operating system course. There are some basics, and here we will go more beyond those basics and touch some advanced topics. But to not leave you completely lost, I will quickly repeat some of those basics. So the basic or the main mechanism which is used to implement a virtualization solution is called trap and emulate. And the idea is pretty simple. You have some code, this can be code either of the operating system or of an application running inside virtual machine. And whenever this code, which executes, like time is going from left to right, so this code executes, and whenever it encounters some instruction, which is, we will call it sensitive instruction, because it cannot be executed directly by the hardware, because, for example, the instruction could cause a reset of the whole computer. This instruction is so-called trapped, meaning that the control is passed to the privileged mode. In our case, this is called hypervisor, so this is privileged software running in CPU privileged mode, and this hypervisor in some way or another somehow emulates this sensitive instruction, and after the emulation is completed, the execution continues by executing normal program as one would normally do. So what is this sensitive instruction? It's quite simple. Sensitive instruction is such an instruction which either changes so-called global state or depends, or its behavior depends on this global state. And by global, here we mean a state which is shared between all virtual machines running in the same physical host. So for example, you may know that x86 architecture has an instruction called hold. This instruction just stops the CPU and waits until next interrupt comes. So it's used for power saving and so on. But if you would allow a virtual machine to execute this sensitive instruction, it would mean that a single virtual machine can stop all the other virtual machines. And you don't want that, because you cannot put the full CPU to sleep from a single machine. You have to emulate this instruction. So if a virtual machine executes this instruction, it needs to be trapped by the hypervisor, and the hypervisor emulates this instruction in such a way that basically it stops only this virtual machine. And by stopping virtual machine, I mean it simply not schedule it again. So if it is a normal operating system task, this task will be in blocked state, it will not be in the scheduler run queue, and will just wait for something. So this is hold instruction, CLI instruction which disables interrupt, it's the same. And on x86 there are also some more tricky instructions. For example, instructions push F or pop F. Those are the instructions which prevented the x86 architecture from being virtualizable in the past, because they change they can change global state and were not so-called privileged instructions. So the simple rule for virtualization, as defined by guys called Popek and Goldberg in the 70s last century, says that all sensitive instructions must be privileged instructions. And privilege means that whenever you try to execute this instruction in non-privileged mode, like in user space, there is a trap or exception, if you want, to the privilege level, and there it can be handled either by emulating or doing something else. Yeah. So that's the basic principle of virtualization. We execute as much as we can normally, and we emulate only things which are sensitive to be executed normally. We have already heard that there is a piece of software which is called hypervisor. There is some misconception about what hypervisor actually is, so I will try to clarify that. Basically, hypervisor is a piece of software which typically runs directly on top of hardware. You can also think about it as the operating system kernel, but this is in this case it's kind of special operating system devoted to virtualization. And then there are virtual machines running under the hypervisor. The virtual machine runs its own guest operating system kernel and then guest applications, and there can be several such virtual machines. So this is so-called bare metal hypervisor. Examples of such hypervisors are Zen or VMware. ESX hypervisors. There are many others as well, and this is useful if you have dedicated hardware in a data center or wherever where you just want to run virtual machines. But if you have something running on your laptop, you want to run native applications, you are maybe not interested in running everything in virtual machines. You want to run your normal applications, and from time to time you run a special kind of application which is a virtual machine. In such a case, you also use a hypervisor, but now this hypervisor is called hosted hypervisor, and hosted means that this hypervisor is somehow a part of the normal operating system kernel. So if it is Linux, you probably have heard something like KVM or VirtualBox. VirtualBox can also be used on other operating systems. And this hypervisor is basically a part of that normal general purpose operating system. And the main idea is like if we have a special purpose hypervisor here, the hypervisor has to implement many services which are also already included in normal operating system. So why not to reuse this functionality? On the other hand, the advantage of this bare metal hypervisor is, okay, so we will have very small, simple hypervisor. This hypervisor will not have a lot of legacy things that will just slow it down and so on. So those are both valid approaches, and people use both. So this was hypervisor. Now, I have also mentioned another term which was virtual machine monitor. Sometimes people confuse the term hypervisor and virtual machine monitor because in many cases this is actually the same piece of software. For example, if you use these bare metal hypervisors, it is often the case that the virtual machine monitor is implemented inside the hypervisor, inside the privileged mode. The reason why it is the case is that it's actually pretty fast, it's efficient, because whenever there is this trap request and something needs to be emulated, it's emulated directly inside the hypervisor, and it's fast. The disadvantage is that it's very insecure, especially if you have to emulate x86 architecture, which like the history of x86 architecture is like 45, maybe more years. So this virtual machine monitor, which emulates x86 architecture, it has millions lines of code because it needs to emulate a lot of weird stuff that were in this x86 architecture in the past. And yeah, it's very complex and so on. The reason why you need that is that people use virtual machines to run old software. They still want to run their software for Windows XP or even MS-DOS, and therefore you need to emulate all these obscure hardware features or processing modes of old CPUs inside virtual machine mode. And because it's clear that the more code you have, the more security problems, or actually the more bugs is there. It's also true for hypervisors and virtual machines monitors. So this structure is not very good for security. For that reason, people started looking at another way how to design virtualization solutions, and they created hypervisors as only the minimum piece of code which can only get the request from the trapped instructions and somehow pass the request to another piece of software which is called virtual machine monitor, and now this virtual machine monitor runs in user space as unprivileged software. So if there is an attacker and this attacker figures out how to attack this virtual machine monitor from a single virtual machine, it means that the attacker can destroy the whole host machine and all the virtual machines running on the host, or can attack all the other virtual machines. If the same happens with this architecture, the attacker only attacks its own virtual machine, and it's quite unlikely that the attacker will be able to go through the hypervisor to another virtual machine, because the hypervisor is really a simple piece of software which just receives the request from the hardware, from the CPU exception, and just sends it or schedules the virtual machine monitor in user space. So that's the basic idea. Now you can wonder why this is drawn in a strange way. So we have the guest virtual machine, the guest operating system and applications, and this is actually drawn inside the virtual machine monitor. In theory, you can have like two boxes, green boxes of virtual machine monitor, green box of virtual machine monitor, and yellow box of the virtual machine. It would also work to some extent, but it would be quite inefficient. The reason is that this virtual machine monitor, it emulates the hardware. And it needs to emulate things like direct memory access. Direct memory access means that if you are receiving, and I will talk about that later, if you are receiving data from your network, the network card, the network hardware directly writes data received from the network to memory, so that you don't have to read them, or the operating system does not need to read them out and copy them themselves. So hardware can access your memory automatically via DMA or busmaster, or there are different names for these. So for the same reason, the virtual machine monitor also needs to have access to the memory of the virtual machine. And this is the reason why it is typically implemented like this, that it's actually an application, and this part of that memory space of that application is actually the memory of virtual machine. And if you are still confused about that, wait a few minutes. I will have example showing how it actually works. So to summarize that, if there is this unprivileged code running either here or in the kernel, which is also unprivileged, and some sensitive instruction is there in the code like hold or CLI or whatever, the CPU generates an exception. The exception is trapped by the hypervisor, and the hypervisor doesn't do anything with that besides passing or jumping to virtual machine monitor, which just emulates this instruction, and then the virtual machine monitor calls back the hypervisor, which then goes back to the original code, which causes the exception and continues the execution there. So this is like the nowadays it starts to be like the common case. So perhaps all of you have heard about QEMU thing, which is often used with Linux KVM hypervisor. So QEMU is exactly this. This is the application which implements this hardware. If you use cloud services, you might have heard of Firecracker, which is also a virtual machine monitor used by or developed and used by Amazon in their cloud. And this is even more lightweight than QEMU to be fast and efficient and so on. Those of you who had operating system course with me, not sure whether it's any of you. Did you have operating system course? Probably not. So you have seen this Nova micro hypervisor that we use there, and this was actually the first hypervisor which shown that this architecture of the hypervisor can actually be faster if it is done well, done right, than this centralized insecure approach. And since then those virtual machines like Firecracker and others started to appear. So this is the basic terminology, and now few comments in general about virtualization before we look at the actual technical details and about how virtualization, what is the role of virtualization and how to write efficient software which runs virtualized. So up to now it might appear, at least if you look at this figure, that to implement virtualization you actually need two kind of privileges, like unprivileged or user space code and privileged code, like operating system kernel or hypervisor. This is right. You really, if you want to implement virtualization, it's sufficient to have just two privilege levels provided by hardware. But it will not be that much efficient as you might like. So for that reason, hardware designers, hardware manufacturers started to develop what's called hardware-assisted virtualization, and what we will talk about next, which is a way how to accelerate this virtualization, and basically it works by introducing more privilege levels. We will see later some detail about how it actually works. So it's important to remember that this multiple virtualization or multiple privilege levels, this is just an optimization. It's not like a requirement. You can do virtualization even without that. It's just an optimization how to make it more performant. And the second thing is, why is virtualization needed at all? Actually, if the operating systems are implemented properly from the beginning, you would not need virtualization. The reason why we need virtualization is that for historical reason, the operating systems, both Linux, Windows, even macOS, they do not implement proper isolation between processes and so on. So if you want to run two applications, those applications basically have to to some extent trust each other, because they are isolated to some extent. But if one application writes files to their home directory, for example to your home directory or whenever, the other application can see the same files and so on. So this is like the default in general purpose operating systems. Nowadays people are developing containers, so we are finally at times where containers are more or less full-featured. They have all the features which are more or less needed. So containers are a way to fix operating systems, to provide better isolation between normal programs. It's interesting that operating systems were initially planned and designed this way from the beginning, but for performance reason they just simply dropped this requirement, because in the past this isolation and security it was not that important. Performance was more important. So that's how it is today. But of course, if you have normal operating system, even with containers, it might be still like too dangerous from security point of view to run the containers next to each other. There are, from time to time, there are still some security flaws, and it's possible to break from one container to another and so on. So still virtualization offers stronger isolation, because the isolation happens at, let's say, hardware boundary, which is kind of I don't want to say exactly simpler or simple, might be a bit simpler, but this x86 is still quite complex. So if we live in the ideal world, virtualization will not be needed. We do not live in such a world, so virtualization is needed. And because it is needed, we need it to be fast, to not slow down our applications unnecessarily. And for that reason, as I have already said several times, hardware designers implemented what's called hardware-assisted virtualization, which is a set of hardware features which somehow, and I will explain briefly how, accelerates the code execution inside virtual machines. There is not a single technology implementing hardware-assisted virtualization. Each hardware vendor has its own technology, which are incompatible. Only if we talk about x86 hardware, meaning Intel and AMD, they both have different technologies. For Intel, it's called VTX. For AMD, I think it's called SVM, or SVM, I think. They basically implement the same thing slightly differently. So yeah, one doesn't have to be confused by that. Then we have other vendors, other CPUs like ARM or RISC-V, and they also implement it differently. The advantage of ARM or RISC-V is that they don't have this legacy of x86 architecture, so they could implement it virtualization in a cleaner way. So while in x86 we have so-called root and non-root operation, and inside each root and non-root operation you have 4 privilege levels, as it was historically developed for x86. So in total you have like 8 privilege levels on x86 architecture. On ARM, it's much simpler. You actually have 4 privilege levels, but for virtualization, it's sufficient to have just 3 privilege levels. One privilege level, the lowest level, is user space for applications. Middle privilege level is kernel space for operating system kernels, and the highest level is hypervisor for virtualization, which is like what makes sense. On x86, it's much more complex because of this history. So let's briefly look at x86, at what's called Intel VMX, which is the technology provided by Intel. And if you look at Intel's documentation and the chapter about virtualization, you will figure out that the core of this hardware-assisted virtualization is something called VMCS. It is a data structure which is stored in memory, and this data structure is managed by hypervisors. So whenever you start a new virtual machine, the hypervisor creates this VMCS data structure, and this VMCS data structure is first created by the hypervisor, but it is also read directly by the hardware, by the CPU. And this is a way how the hypervisor can communicate with the hardware, how they notify each other about what happens, where, and so on. And by reading or writing to this data structure, they can just implement this hardware-assisted virtualization. So, how it actually works and what is some terminology that we will need to understand the next slide. So I have already said that there is something called root operation and non-root operation. So to understand that, just remember that before 2005, x86 architecture was not virtualizable. It was not easy. People used some tricks like binary translation of operating system code and many nasty things, which somehow made x86 virtualizable, but it was like, yeah, it was not nice. So, but Intel wants to still be compatible with this old mode. So this old mode, how x86 CPUs behave since beginning, is called root operation. But this root operation is not suitable for running virtual machines. Therefore, if Intel wants to run a virtual machine, they have to switch a CPU to so-called non-root mode or non-root operation. And it looks more or less like the root mode. The only difference is that all sensitive instructions are privileged. So if you remember, I talked about this popf and pushf instructions, which are sensitive, but they were not privileged in root mode. So in this non-root mode, they somehow changed how those instructions behave, and they behave that they always strap to the privilege level whenever they are executed in non-privileged mode. So on x86, the CPU can be in one mode or in another mode. If it is or if it goes into this non-root mode, it goes there through an operation which is called VM-enter. There are special instructions implemented by the CPU, either the instruction VM-launch or VM-resume, and if you execute those instructions in root mode, they just switch the CPU to non-root mode and execute like inside a virtual machine. On the other hand, whenever the virtual machine executes something which needs to be handled by the hypervisor, either if the virtual machine executes VM-resume or VM-call instructions, or if it executes any other sensitive instruction, then the hardware switches back to the root mode, which is basically the hypervisor, and this operation is called VM-exit. And what happens whenever there is a VM-exit? The hardware fills some fields in this data structure, which is in memory, and whenever the hypervisor gets called because of this VM-exit, it looks into this data structure. It can check the get state, it can check the fields VM-exit information, so it can figure out what happened inside virtual machine, why there is this VM-exit. And this can be, for example, that the virtual machine called this VM-call instruction, which is something like system call, but it's a call to hypervisor, or because the virtual machine executed some sensitive instruction, the sensitive instruction needs to be emulated by the hypervisor, and what and how can be emulated, the hypervisor can learn it by reading the fields in this data structure. So this is the basic principle. And one of the one of the key insights from this slide is that if you want to run your virtualized workload efficiently, you want as little as possible VM exits and VM enters. So every VM exit, every VM enter has some overhead. The hardware needs to write to this data structure, the hypervisor needs to read this data structure and do something, and it's some overhead. So if possible, if you can run your workload without any VM exit, this is all executed natively by hardware, and there is no, it runs as fast as possible. If for whatever reason, and we will talk later what those reasons could be, if you have a lot of VM exits, your execution is slow and you don't like it. So this is the basic principle of switching between root mode and non-root mode on x86. Now, and this is one source of overhead, this VM exits. Another source of overhead is access to memory. So now we will look at how memory is accessed from virtual machine and what can slow down this access. And the thing is called nested paging. If you remember some operating system lectures, you have probably seen something like the left half of this picture. So you have physical memory inside your computer, and you know that your programs, your processes, and the operating system, they implement together with hardware something which is called virtual address space. And this virtual address space means that each process has its own virtual address space, which represents memory where this process can write. And if the process tries to write somewhere else, it is the hardware just generates some exception which is called page fault, and the operating system can handle this. Typically, the application executed some invalid instruction or whatever, and the application is closed, or by implementing some copy on write or other things. So you probably know how is that implemented technically, that the CPU contains a piece of hardware which is called memory management unit. This memory management unit implements something which is called page tables, which is basically a tree-like structures. And if you have a virtual address, by using those page tables, you can, or the CPU can translate this virtual address to physical address where the value is actually stored in the memory. And you should probably know how it actually works. So this is a picture showing what happens on x86 if you have a virtual address, and how it gets translated to physical address. So depending on how big hardware you have, you can have either 3 or 4, and nowadays I think even 5 levels of page tables. So in the worst case, if you have the address, then you or the CPU needs to read up to 4 locations from memory to actually translate this virtual address to physical address, because if we go from the lowest level is page table, so we have to, or the CPU has to look into the page table, then page directory, and I don't know those acronyms, what they mean, PDP, page directory parent probably, and PML4. This is like just another level of this tree structure. So here we have just 3 levels. Here on this picture we have just 4 levels. So in the worst case, if you read or write memory from your application, the CPU needs to read or write 4 times more memory to translate this address to physical address. This is if this is all the time, this would be of course very, very slow. So for that reason, CPUs implement caches. Those caches, you have already heard about them. Those caches are called TLB, Translation Look Aside Buffer. And once the CPU reads all those page tables, page directories, and so on, it caches the result into TLB. So next time when you access the memory from the same page, you don't need to do this what's called page table walk, and you just look into this cache and you have the physical address directly. So this is the situation without virtualization, with classical operating system and classical memory management unit in hardware. Now, if you have virtualization, basically what this hardware-assisted virtualization implements is this second part. If you look at that, it basically looks the same as this left part, but it's just another not level, I would call it layer, let's say, another layer of page tables. The difference between those guest page tables and host page tables is that those host page tables are set up by the hypervisor, whereas those guest page tables are set up by the guest operating system kernel. Because remember, we are talking about virtualization where the virtualized operating system doesn't know that it runs on virtual hardware. So it thinks it runs on real hardware, therefore it wants to configure their own page tables and so on. But those page tables live not in physical memory, they live in so-called guest physical memory, which actually is called also host virtual memory, and there is another level of translation between these. So how does it look like from the performance point of view? Here, if you don't have this translation from virtual address to physical address cached inside TLB, you had to read four values from page tables, or the CPU, the memory management unit of the CPU. Now, if the same happens inside a virtual machine, the situation is more complex. Because for reading just this value of the guest page table, you might, in the worst case, need to traverse the same four memory accesses to host page table, so that you can read this single value from the guest page table. And this is just one level in this guest page table. For the second, third, and fourth level, you have basically the same. So in the worst case, if you access a memory location from a virtual machine and nothing is in TLB caches, single memory read or write can read into 24, if I'm not mistaken, 24 memory accesses due to reading or writing, or actually reading page tables, which is known as page table walk. So the conclusion is that in virtual machines, TLB misses can be much more expensive than outside of VM. Yeah, I think this is quite old benchmark. I believe that nowadays the numbers are a bit better, but still there is even today there is a measurable impact. So for Intel, these I don't know, 15 years ago when this technology started to appear, the overhead of Intel CPU was 15%. AMD's at that time, AMD was much worse in that regard. Like the memory access overhead, if you have a lot of TLB misses, was 38%. I believe that now the situation is better. I would say that both vendors are somewhere around like 10%, but still there is some performance penalty. So if you are not happy about this penalty, there are some things you can do. You can either buy better hardware, Nowadays, here is written like tagged TLB. This is hardware feature which like 15-20 years ago it was not that common. Nowadays all CPUs are designed like this, meaning that you don't have to flush TLB caches whenever you switch execution from one VM to another. In the past it was you had to flush all the caches, so after every context switch between virtual machines it was you paid this this extra penalty. Nowadays it's no longer the case, but if you want to not have this penalty, you just need to buy CPU with bigger TLB caches. So all the server CPUs, they typically have more TLBs. So that's one thing. You cannot do this as a software developer. You can do this by buying better hardware or renting better hardware. What you can do as a software developer, you can try to use what's called huge pages on Linux or super pages in other operating system. Basically, if you don't do anything, typically operating system uses so-called or not so-called, page sizes of 4 kilobytes, meaning that all your memory is allocated on 4 kilobytes chunks, and for one 4 kilobyte page you need 1 TLB. If you need a lot of memory, you need a lot of pages, you need a lot of TLBs. If you don't want to run out of TLBs, you may talk to operating system and ask to allocate or to back memory not with default 4 kilobyte pages, but with some bigger pages. So on x86 this is typically 2 megabytes, or I think even 1 gigabyte pages are for those 4 level machines. So you can ask the operating system to do that. In some cases, the operating systems have some heuristics how to allocate this automatically. Sometimes it works well, sometimes it doesn't work well. So it's always better if you do it explicitly and if you ask for big pages, because then you do not run or experience that many TLB misses by accessing the same amount of memory. You also may have heard that some modern CPUs like Apple's M2 or whatever, they offer even page sizes which are not 4 kilobytes. There are bigger page sizes, and it can be configured. I think even other architectures offer these features. So it turns out that the 4 kilobyte page size is too small for today's systems, and things like TLB misses and so on are problematic. So if you want your software to run efficiently, you have to think about both like hardware well designed for virtual machines and also software to optimize not only for cache misses but also for TLB misses, because TLB misses are more expensive in virtual machines. Okay, so now is the time for our small example. Those of you who visited our operating system course have already seen it, so I hope there is, I think there are some people who didn't see it, so I will just try to show it. Yeah, so you see something. Okay, so what I have here, I have an implementation of minimal virtual machine monitor. This minimal virtual machine monitor is a simple C program which uses KVM hypervisor. And for you to imagine how this VM exit, VM enter actually works, you can just look into this code. There are some comments, and if you look at the bottom, you will see that this is like 100 lines of code, including the comments. So it's really the simple piece of code. And with this simple piece of code, we can actually execute a virtual machine which is implemented in this assembly code. To make it really simple, I just implemented, or it's not my implementation completely, but this is taken from some website. So this virtual machine is like the really simplest virtual machine. There is no operating system, nothing. This is like just a piece of assembler code which performs some I/O. And this I/O is not network communication that we will talk about in a while, but this I/O is writing to serial terminal, serial port, like serial port. If you look into this code, you will figure out that there is a loop. There is this jump which goes to the next instruction, and there is an out instruction, and out instruction simply it's x86 instruction to do I/O, O like out, and this basically writes a character to serial port. And which characters are written? It's written in here in this message. So this code just writes all the characters in a loop one by one from this string to serial line. So if you compile this code and run it on a bare metal computer and connect serial terminal, you will see hello world. But now we will write, or I will show you virtual machine monitor implemented via KVM, which just creates a virtual machine and does the same. So I will go through it quite quickly. If you don't understand anything, either ask if you are here or just look at the Linux documentation. But I will try to give you some high-level picture. More details. I have more details in my operating systems lecture, which I referred at the beginning of this lecture. So we start by opening a file /dev/kvm, which is a way how an application can communicate with the KVM hypervisor. In this code, I have those check macros. Those check macros are just simple macros. If this fails for whatever reason, it just calls exit and prints some error message, so that we don't have to deal with error checking. So I open a communication channel, which is a file descriptor to the hypervisor. I tell with I/O control, this is a way how to send some request to the hypervisor. So with I/O control, I tell the hypervisor, please create a virtual machine. With this virtual machine, file descriptor, I can then tell the hypervisor what to do with the virtual machine. But before I do that, I first allocate the memory which will represent the physical memory of that virtual machine. Or it's not like physical memory, but it will be this guessed physical memory. For this small virtual machine, we just need 4 kilobytes, so one memory page of this memory. Then we open the file which will be the code running in that virtual machine. So this file gets compiled, and it is stored into this hello.bin file. So I will read it and store it to this memory. And then I will tell the hypervisor, I will send the hypervisor another request. This another request is called set user memory region, and basically this tells the hypervisor to set up the page tables in such a way that the memory I provided here with this mem pointer appears at guest physical address 1000, and it's just 1000 hexa 4 kilobytes of memory pages. So this way I tell the hypervisor to set up the page tables. Then I tell the hypervisor to create a virtual CPU. With this virtual CPU, I also ask the hypervisor to give me access to some control data structure. You can see, if you remember this VMCS data structure, which I have talked about, how Intel implements this. KVM implements some kind of generalization of that structure, which is the same for all supported solution. So I can just tell it to map this data structure to my memory so that I can see what was the reason of VM exit and so on. And then I tell the hypervisor to set the registers of my virtual CPU, which are necessary for executing the code. So I do it once. Here I do it for the second time for the other registers. I set the instruction pointer to address 1000, which is where my application starts. And then this is the main loop of the hypervisor. Here I execute kvm run, which is basically this VM enter. If I execute this system call to kvm, kvm then executes VM launch instruction or VM resume, depending on whether I'm in the first iteration or in the later iteration, and the CPU just switches to non-root mode operation and executes the code of the virtual machine, which is this code at the right. Once this code executes this out instruction, this is sensitive instruction because it's talking to the hardware. So the hardware performs VM exit. If the hardware performs VM exit, it notifies the kernel KVM hypervisor, and we appear from this function call. We can look at this run data structure, what was the reason for exit. If the code executed halt instruction, which you can see here, we just return. This is not our case now. If the code executed some IO instruction, we can ask the hypervisor what was the port number and what was the size and so on, and we emulate writing to serial port by calling normal puthar function. So puthar just prints a single character to standard output, and this is how we emulate this sensitive instruction out. Once we emulate this instruction, we return back to the end of the while loop, and we continue by again calling kvm run. This will be another VM exit, and the code of the virtual machine starts executing. And this way we just emulate the whole virtual machine. So if you want to see it in action, we can compile it. It's a very simple C program, so nothing fancy. We compile this assembler, produce this hello.bin, and we compile this kvm test and produce just kvm test binary. And if I run it, it prints hello world, and that's it. This doesn't look fancy, but if you see what's behind that, it's full virtual machine. It emulates IOs and so on. So that's it. If there are any questions, just ask, and if not, we can continue. And yeah, we can continue, and now in the rest of the lecture I will talk about I/O virtualization. So we have seen very simple I/O virtualization in the example for serial port. So serial port writes were emulated with puthar. Now we will look at the real thing, how to do emulation or actually I/O with networks, because networks are perhaps most important nowadays. The other important I/O is storage disk, but basically this is quite similar to network, so we'll do just network, and storage is similar. So to understand how to get fast I/O with networks, we first need to understand how network hardware actually works. So this is some network card which you can plug into your PCI slot and communicate over network. I will call it network interface card in this, and will abbreviate it with NIC, like network interface card. And now what happens if you want to transmit some data over the wire or optical cable or whatever? So basically, you as an application, with the help of the operating system kernel and the device driver, you write your data you want to send somewhere to memory. So if you are writing your application, you write it to memory, you write send or write system call or whatever the system call is called on your operating system. And then the operating system kernel copies your data to some memory, some network buffers inside the kernel, or if you use some zero-copy networking, directly the memory used by your application can be used as this packet data. Then the device driver somehow maintains what's called buffer descriptors, or it can be called differently for different pieces of hardware. This is some data structure which is shared between the device driver and the actual hardware. The device driver writes their information about what the hardware should do, and the hardware does it. So the device driver, if you want to send this packet of data, so the device driver writes there the pointer to the data, what is the size of the data, and some other information, so that the hardware knows what to do. If you want to send multiple data packets, you just write them somewhere to memory and put there all the pointers to your data. Once everything is set up, and I am saying you, but by you I mean like the device driver called by your application. So once everything is set up, the device driver writes to registers of the CPU, so of the network interface card. So the registers of the network interface cards, those are different things than registers inside the CPU. Those are things somewhere here inside the chip on the card. And to write to those registers, you write to memory mapped area where this write gets translated through PCI bus, and basically the CPU is sending through PCI bus to this network card, hey, the software just writes to this register. So here we perhaps want to write to a register which is usually called something like TX-tail, meaning we are saying those registers from up to here, which is TX-head, until or before this one, TX-tail, those are valid descriptors containing valid pointers to data, and you should send those data. And once you do this right, the hardware starts reading those addresses and starts sending the data in, which is in memory, outside to the wire, and just sends it out. So to summarize this, if you want the hardware to do something, you just write data to memory, then you write to registers, which from the software point of view also looks like writing to memory, and then the hardware does what it is supposed to do. Now with receive operation, it's very similar. Instead of writing the actual data to send, you just allocate empty data buffers. You put the pointers to those empty data buffers again to buffer descriptors. Now this is like the same picture, but actually here we should have Rx head, Rx tail arrows here. You, by writing to those registers, you tell the hardware whenever there is some data received from the wire, you just store them by using DMA, direct memory access, to the memory located here. And once the network card stores the data, either all or just one. Typically there are some timeouts and so on. It generates an interrupt, and the interrupt is handled by the device driver. Whenever the device driver receives an interrupt, it looks into these packets and just pass them to other parts of the operating system, like network stack and so on, and these data are then copied to your application. So this is in a nutshell how modern network card works. If you have disk, it's basically the same. The thing here are not packet data, but those are the data you want to write or read to the disk, and so on. With network card, it might be actually more complex than what's written on the previous slide, because most modern cards implement something called scatter-gator DMA. It can compose the packet from multiple independent pieces. Typically, you just need to concatenate like headers, like IP Ethernet addresses with the actual data. So the hardware can does this concatenating yourself nowadays. You don't have to do it in software, like put the headers here and your data just behind it. The hardware can take header from here, data from here, and connect it together while sending it outside. Yeah, so this is how the hardware works. And now how we can emulate such a functionality in a virtual machine monitor. It's quite simple. We have seen that all of this is just writing to memory. From the software point of view, if you look what the device driver of a network card does, it's just writing to memory and handling interrupts. So what needs to be done if we want to emulate a network card in a virtual machine? We just need to trap all accesses to registers of the network card. So basically, whenever the device driver running in the guest operating system kernel writes to the area where there would be normally registers of the network card, CPU executes VM-exit, because it will see there is a write to memory which is not physical memory or not real memory. So there will be VM-exit, and our virtual machine monitor will see there is VM-exit on this memory address, and it will see, this memory address, this is where I emulate the network card, so there is something to do with the network card, and it can then follows those pointers written by the guest operating system, find where are the address of the data of packet, and then in a simple virtual machine monitor like we have just seen, can emulate this network communication by just creating a socket and just sending the data from memory of the virtual machine via normal send system call over the socket. So this you can do it, or all the virtualization solutions implement a method like this, but it's sometimes it's not very efficient. The reason why it's not so efficient, there are many reasons, or there can be many reasons. One is that maybe your hardware that you used is not easy to virtualize. In the simplest case, if you want to virtualize hardware like this, to send data, it's sufficient just to write a single register like here, txtail. The device driver just writes to this register, telling either the hardware or the virtual machine monitor, I have just added some entries here into this table, please send the data. So if it is like this, it means like a single VM exit per packet or per set of packets. Some network cards, typically those older ones or not server cards, they can implement those registers not in such a clever way. There can be several VM exits per a single packet. So if you have network cards like this, when sending data out requires multiple VM exits, throw it away because it would be very inefficient when running it in the cloud, or when running I/O-bound applications in the virtual machines. So definitely you want a network card with at most single VM exit per packet. Yeah, so this is if you have such a network card, it's good, but still still it's not if you have virtualization solutions, it's a bit unnecessary to emulate real hardware network interface card, because it means that in the guest operating system you need to have the device driver for that emulated card and so on, and the real hardware is typically much more complex than what's actually needed for the virtual machine to send the data out. So for that reason, operating systems and hypervisors implement some kind of interfaces, how for example network communication or even storage I/O can be handled more efficiently without actually emulating the real hardware. On Linux, one such technology is called VirtIO, and the idea is very simple. So basically, nowadays all the hardware looks more or less the same. The applications or the operating system writes some data to memory, then some pointer to some register, and then the hardware reads the data from memory and does something with the data. This something either sends data to network or store data to your disk or sends some images or video or whatever to the GPU. Basically all the hardware looks like this, like the network card that we have seen. So why to implement one virtual driver for virtual network card, another for a virtual disk, another for a virtual GPU? Because it's more or less the same. Those things just need to exchange the data between the virtual machine and the the host operating system or hardware. So in Linux they implemented VirtIO. This is basically a simple ring buffer where guests or hosts can write data and the other side can read it quite efficiently. And on top of this VirtIO, there is VirtIO Ethernet, VirtIO disk, with VirtIO serial card, maybe, I'm not sure, but maybe there is even VirtIO GPU, and so on and so on. Other operating system implements something similar, and it's very efficient. It's very efficient because it usually works out of the box. You don't have to find the good driver and so on, and then mess up with different versions of drivers, emulations, and so on. But still, it has still one disadvantage from performance point of view, and this disadvantage is that we still have one VM exit per, if you are talking about networks, per, for example, transmit operations. So you cannot have virtual machine which just runs without any VM exit as fast as possible, achieving high performance. If you want to have this, and usually people want to have this, you want to avoid the software emulation completely. You want to go directly from the virtual machine to the hardware. You can do that, and this is called PCI pass-through. Basically, you can give the virtual machine direct access to your PCI device, to your network card, and it can send or receive data directly without software intervention. But it's not that easy. The problem is that hardware works with physical addresses. And as you know, virtual machines do not use physical addresses. Virtual machines use virtual addresses known as host virtual address or guest physical, and those addresses do not match those addresses used by the actual hardware. So if you have the guest operating system running here, which thinks it runs on real hardware, then this will not work because the real hardware will actually see the addresses at a different place, because there is this extra mapping managed by MMU inside the CPU. If you try to do PCI pass-through on hardware which doesn't support it, what happens is that, for example, the device driver of inside the virtual machine writes to NICS registers that there is a buffer in memory with the packet data, and then the network card will just read data from physical memory at the same address as this virtual memory. But it can be the case that this virtual memory is not mapped to the same address in physical memory. It will be quite likely. So this is a severe security problem, because either your virtual machine can cause sending random data from physical memory of your host machine, for example, some encryption keys of your disk or whatever, over the network out, or even worse, by receiving data from network, this virtual machine could overwrite whatever memory inside the host system, either the hypervisor or another virtual machine or whatever. So this is very dangerous, and you cannot use it without some special hardware support. And this special hardware support is called differently by different vendors. By Intel, it's called IOMMU, which is another memory management unit. Now, this memory management unit is not implemented inside CPU hardware, but it's implemented inside chipset. Or nowadays, chipset is even inside CPU. It's called PCI root complex, but it's actually somewhere else on the chip. And the principle is that this this memory management unit makes it appear so that devices like the network card sees the same memory mapping as is used by the virtual machine. So if the virtual machine thinks I am writing to this address, then the hardware will get the same translation to the physical address, so that this address and this address from the virtual machine point of view and device point of view will be actually the same address in the physical address space. So this technology in case of Intel is called VTD, which stands for Virtual Technology for Devices. This adds this another level of memory address translation. These page tables needs to be managed by the hypervisor, this VTD, and similarly to this VTD, there is another piece of hardware for managing interrupts, and only if you have this hardware, only if you have the hypervisor which supports that, which nowadays most of the, I think, like production hypervisors supports that, then you can use this PCI pass-through. Nowadays it usually works. I remember times when this technology was quite new, and every second hardware, even server hardware, has this implemented with bugs, so it was quite easy that sometimes your whole computer just locks up and it didn't work. Nowadays hopefully it's all right, it works. And usually you don't buy your hardware yourself, you just rent the hardware from the cloud provider, and they probably know which hardware to buy and which hardware works well. So this is how to implement PCI pass-through. It is nice, there are no VM exit, virtual machine can run uninterrupted, communicating as it wants. The problem is that if you want to have more virtual machines, because that's the point of virtual machines, you can basically share a big server with smaller virtual machines, maybe between multiple customers, and to utilize all the hardware efficiently, You just want the hardware to be shared by the virtual machines. With PCI pass-through like this, you can't do that because there must be one network card per VM. But people want this. People want to have like PCI pass-through and have multiple virtual machines running on the same host. So hardware designers came and implemented something which is called single root I/O virtualization. And the idea is pretty simple. Remember when I talked about VirtIO, what VirtIO or whatever other emulation of a device does is that you get requests from multiple virtual machines and you multiplex those requests to a single network interface, and you do it in software. If you do it with VirtIO or if you do it in virtual machine monitor by emulating some real hardware, it's the same. You are just doing this multiplexing in software. What single root I/O virtualization is basically that this multiplexing of sending and receiving data between virtual machine is done in hardware. A network card which implements this single root I/O virtualization looks like this. It has some unit which is called physical function, abbreviated by PF here. And this PF is the thing which has connected the connectors or wires or cables or whatever and can communicate physically with the network. This physical function looks like normal network card. If you want, you can use this physical function as a normal single network card. But besides this physical function, the network card has also several, typically 8 or 16 so-called virtual functions. This virtual function is not a full-fledged network card. This is basically just a set of registers like this. So this virtual function is the set of registers which you can map to the virtual machine, and each virtual machine has its own set of registers. But this set of registers is not connected to real wire. This set of registers is there just to allow the software to write to them. And then there is some kind of multiplexing implemented in the hardware between those multiple virtual functions and the physical function. So whenever this virtual machine writes a packet to memory and updates the tail register, this tail register causes this virtual function to send the data from memory to physical function and for transmission, and then there is some kind of scheduler which goes over all virtual functions, and if there is some data available, some packets available for each virtual function, it sends the data through the physical function. So this is now what you find in most cloud providers, especially if those more expensive ones where you just want the highest performance, or not most, but more expensive. Maybe the cheapest one have something simpler. But if you want high performance, this is what's used. You can get a virtual machine. This virtual machine gets assigned a single virtual function, and you can run your applications without VM exit and communicate over the network. Yeah. So this is the very efficient, scalable. Scalable. It's not scalable because if you run 1,000 virtual machines, you run out of those virtual functions, because those are these are like physical entities in the hardware. So it's not scalable that you can run as many hardware machines, but I mean that there is no bottleneck caused by software in performance. And the last thing, which I will just go over very quickly, if you communicate between from virtual machine, you can either communicate between physical machines by using, for example, this PCI pass-through or single root I/O virtualization, but often you just need to communicate between different virtual machines. And in that case, you can still communicate over the virtual function. It's still possible that you send the packet to virtual function, and this virtual function, instead of sending it to physical function, sends it just to another virtual function, and the packet gets received to another virtual machine. It works, it's fast, but still it has to go through the PCI, and PCI, especially for networks, is usually not as fast as memory. So if you want to do just inter-VM networking between different virtual machines, you don't need all this hardware trickery. What's typically used, some kind of software-based switches, which are not only efficient but can be also configured in some way. And again, typically these are implemented as a special applications. Either these applications shared some memory directly with the guest operating system, so that it can perform zero copy optimizations, and actually communicate either without any copying or with just one copy between the virtual machines, which is the fastest thing you can get. And the last thing, which I almost don't have time, is that there are several, even with those software-based switches, there are ways how to optimize this communication even more. If this switch implements some hardware features which basically allows to, it's called, for example, TCP segmentation offload or large receive offload. Those are normally features or originally used for hardware network cards, which allows more efficient handling of multiple packets and higher throughputs, like if you have gigabit or 10 gigabit network card. Without those accelerations, you cannot reach the full bandwidth. And interesting thing is that you can use the same techniques inside your virtual switch, software virtual switch, and if you do that, it also increases the efficiency of this virtual switching solution. So you want to configure all these optimizations, offloads, and so on. And with all of that, you have very fast, very efficient inter-network communication. So that leads me to the conclusion. Virtualization is just another layer of indirection, which means that it only adds overhead. Nowadays, or if operating systems are done properly from the beginning, you would not need this virtualization. But if you have it, and if you just need to use it for whatever reason, you should just know how to decrease the effect of this overhead, or decrease the overhead as much as you can. And we have seen several techniques how to do that. Use huge pages, use efficient network interface card models like VirtIO, or even remove the emulation at all by using hardware features like PCI pass-through or single root I/O virtualization. That's all from my side. Thank you for your attention. Next week you will see David Šišlák with his last lecture, and then we will see us together at the exam. Thank you and goodbye.